Hi guys. In this NMR video I will cover carbon NMR. Carbon NMR very useful. We will be looking at the carbons in the organic molecule. Okay, let's go through the handout page here. Now the spin quantum number for carbon 13 is 1/2. We noted that before. And we also noted that carbon 12, which is the more abundant isotope, the spin quantum number is actually 0. It does not have a net spin. Thus, carbon 12 does not have a magnetic moment, the nucleus, and it's thus not NMR active. But we can do NMR on carbon 13 because it has 6 protons, but it has 7 neutrons. So one of those subatomic particles is odd, and thus it will have a spin, and the spin is actually 1/2, just like proton. Okay. But carbon 12 is 99% of the carbons out there in your body or in a sample. Okay. 99% of the carbons in this molecule here, this compound here, are carbon 12, but 1% of them, about 1%, are carbon 13. And it's that 1% that we're able to do carbon NMR on. But because only 1% essentially of your compound is NMR active, carbon NMR is much less sensitive than proton NMR. Because of this natural abundance of carbon 13. Thus, carbon NMR requires typically more compound when you do the analysis and or longer runtime. That is, more scans. Okay? Now, for typical proton NMR, we use about maybe 5 milligram of compound, and we usually do 16 scans. Okay? HNMR. Now you could run the carbon NMR on the same sample. Okay? You could prepare your sample here in an NMR tube, and you could run proton and carbon on it, 5 milligrams. It's going to take you much longer though. For carbon NMR, okay, I could say 5 milligrams. You could do that. But often if you're going to run carbon, you want to increase this up to maybe, I don't know, 10 to 20 milligram. Or even more. But then you're going to run more like about 500 to even maybe up in the order of 5,000 scans. Okay? Because again, only 1% of the carbons in your tube here, in your molecules, are NMR active. Okay. Let's go through this here sort of systematically first. What type of information is obtained from carbon NMR? Very similar to proton NMR. Number 1, carbon NMR can tell you the number of non-equivalent carbons that you have in your compound. And that's essentially what proton tells you. Proton NMR, number of non-equivalent protons. Because each signal represents a unique carbon in your compound. All right, this is so basic it may take a little bit to think about it, but each type of H gives a signal in the HNMR. Each type of carbon gives a carbon signal in the carbon NMR. Now one thing, in carbon NMR, our signals are all going to be singlets. Okay? Singlets. Why? That's because the splitting is typically removed. We'll talk about this. You can get the splitting. But the normal carbon NMR experiment or setup is done via or by proton decoupled. We remove the coupling to the protons. Because in carbon NMR, it's the protons that split, the H's that split, all right? And they split just like in Proton NMR by the N+1 rule. We'll talk about that. But there's a tricky way that we can actually remove that splitting. We can decouple the carbons from the H's by manipulating the experimental parameters. Now, I'm not going to get into all that. If you ever take an advanced course on NMR, you would, of course, get into that. But because we decouple it, we remove the coupling to the protons, all peaks in the carbon NMR are actually singlets in a typical NMR. Now, you can keep the coupling. You can run a carbon NMR and keep the coupling or not do proton decoupling. If you keep the coupling, you would get splitting, and it's the H's that are on a carbon that is directly bonded to the carbon being observed. Those are the ones that will split the carbon signal. And they split, of course, by the N+1 rule. For example, let's look at this compound here, N-propyl bromide, or we could call it 1-bromopropane. How many unique carbons, or non-equivalent carbons? 3. 1, 2, 3. And thus we expect 3 signals in the carbon NMR. Okay, we're looking at the carbons, not the H's on the carbons. If we're doing a standard proton decoupled experiment, it's going to be 3 singlets. But what would these signals look like if we kept the coupling? Again, the coupling comes from the H's on the carbon that's being observed. The carbon on the end here has 3 H's. Those H's will split the carbon according to the N+1 rule. 3 plus 1 is 4. This will be a quartet. This carbon has 2 H's. 2 plus 1 is 3. That carbon would be a triplet. And the same for this carbon, because it also has 2 H's. And so if we kept the splitting, we would have 2 triplets and 1 quartet. Okay? So, number of signals. And we can also tell, depending on the location of those signals, what type of carbons we're dealing with, just like with proton. And so we have tables which show chemical shift values, ppm values, or so-called delta values. Now, if you know your proton chemical shifts, you really are halfway there in learning these. And we can make use of the so-called 20x rule, which states that the carbon will give a signal at a ppm that's about 20 times the corresponding proton signal. Protons on that carbon. So for example, benzene, we know that the aromatic H's are about 7 ppm. Thus, the carbon in which that H is on is going to give a peak roughly at 20 times this, which would be about 140 ppm. So that's using the 20 times rule. I can do an example here. We know that this CH2 group would be about 3 to 4 in the proton NMR because of the deshielding by the electronegative bromine. The H is here. The corresponding carbon would thus be 3 to 4 times 20, and that would be 60 to 80. Now, if we look in a table, that's going to be like right here. Carbon bonded to like a halogen with Z. And there, two generics here, Z, and then a definition of Z is NO, or another generic, X typically being halogen. And they say 30 to 80. Our 20 times rule put us about 60 to 80. Now the 20 times rule will put you on the high side. It's actually closer to maybe the 17 or 18 rule. But still, it got us in kind of the range. All right. Aromatics Alkenes, remember, about 5 to 6. In Proton Nmr, if we multiply that by 20, we're at 100 to 120. Okay. Very important for carbon NMR is we can see the carbonyl group. C double bond O, because it has a carbon. And a carbonyl typically gives a signal in the carbon NMR at about, some people say roughly about 200. But it can be lower or more upfield from that. And this table says about 160 to 210. We can use our 20x rule. The only carbonyl with a hydrogen is going to be an aldehyde. But this is, if you remember, about 9 to 10 ppm. And thus the corresponding carbon that H is attached to, about 20 times this, so that gets us about 180 to 200 ppm for the corresponding carbon. And you see it gets us in the range, okay? It's never going to be exact, but approximate range there. And usually we can only see the carbonyl in the IR, but we can also see it in the carbon NMR. Because typically nothing else is going to give a signal this far downfield in the carbon NMR. Okay? All the other signals are more upfield. All right, a comment about integration. Integration is not that reliable in carbon NMR. Very reliable in proton NMR, and we use it extensively. But not so much in carbon NMR. That is, the area under the peak for each signal does not always correspond to number of carbons, as it does with proton NMR. The reason why not is because of variable relaxation rates for carbons. What's a relaxation rate? Let's turn back a little bit. If you remember here, we can get an absorption by flipping essentially the alpha state to the beta state. Okay? It's called a spin flip. Inline, it absorbs energy, and we can get the nucleus, the magnetic moment of the nucleus, to flip and become oppose the external field, higher energy state, but we can make that happen. And we can plot absorption. But actually in the modern instruments, what we actually plot is the relaxation. We don't plot what's absorbed. We plot what's given back out, given back off. The energy that comes back out whenever the nucleus does a spin flip back to the lower energy state and gives off energy. It's called relaxation, and that's actually what we plot. All right? theoretically, the absorption should equal the relaxation, assuming there are no other physical mechanisms for transfer of energy somewhere. Variable relaxation rates. Okay? That is, for different carbons, the energy comes back out at different rates. Well, how does that affect integration? Okay. Let's see if I can illustrate this. We have two different carbons. We have carbon here, carbon A, and we have carbon B. Let's say this one relaxes. Okay, relaxation. Okay. We pump in the energy, it absorbs. Okay. The radio frequency. Then it's going to relax. The energy is going to come back out as the spin flip goes back down to the alpha state, and that's what we plot. But the energy comes back out, and let's show that coming back out maybe as a sine wave. Okay, the energy is coming back out. Okay, and it sort of tails off. Now, other carbons may relax at different rates. Let's show this relaxing much slower. The energy is coming out. But it takes longer. Okay, this is time. It takes longer for the energy to come out for some reason. Okay, now there's reasons here. We may not go into exactly why. I'll explain a little bit. Now this is one scan. We pump in the radio frequency, it gets absorbed, spin flip, but then it flips again and the energy comes back out and we measure it. Energy comes out. But remember, we're going to run 500 to 5,000 scans. Between each scan, we measure energy coming back out. But the typical experiment, you only measure the energy coming out for maybe a few seconds. Let's say here. Okay? And this is going to be in measurement for scan number 1. Well, guess what? For carbon A, we measured all the energy. It gave a full signal. Okay? But for carbon B, we didn't get the full signal because we stopped the measurement before the full signal came back out, before it fully relaxed. Partial signal. And so when you plot this, two different peaks, one may be like this, and by the way, in carbon NMR, they're much sharper. There is area under this curve, okay? And the other one may look like this. Full signal, partial signal. But they're both one carbon. And if you integrated this, it might be a 3-to-1 ratio. And you would say, well, that's 3 carbons and this is 1? No. In Proton, yes, that works, but not in carbon NMR because of different relaxation rates. Okay? Now you could say, why do we stop the measurement here? Why don't we measure all the way out until this one is fully relaxed? Then both signals would sort of be equal in terms of energy release. Well, if you did that, 500 to 5,000 scans is several hours to overnight. Think about IR. It takes you usually run 4 scans. It takes you 1 minute to run the IR once you get your compound on the IR. Think about running an IR for several hours or overnight. Okay, and this is with short sort of measurement intervals. If we expanded this out, we're going to turn this into like 2 or 3 days running. And that's just too long for a typical scan. We could do that, but the typical scan has short measurement intervals, largely because of a time restraint. Okay. Now, we can actually use this idea to our advantage, though. Okay? It turns out that carbons with no hydrogens on them relax very slowly. Thus, the signal for these types of carbons are often noticeably short or less intense. Back over here, likely a carbon with no H. Okay? Because those are the ones that are going to relax slow and end up giving you a short peak, which is what I will call them. Okay? A short peak. All right? We will refer to that. Okay. Couple of illustrations of things we talked about on the first side. Number of scans. Why do we have to run so many scans? Well, we discussed that, but let's look at a comparison. Here are 2 carbon NMRs of the same compound, and it's the same tube, okay? Same concentration, everything. The top one is 65 scans, and the bottom one is 5,000 scans. By the way, baseline 0 to about 200, 220 ppm. Okay, but look at the difference. Look at the difference in the baseline for the spectrum. This baseline is much more noisy. Okay, noise coming through here. And because it's noisy, you can't always tell what is a peak and what is noise. All right, we have some peaks here, but if we run more scans, such as 5,000 in this case, the baseline becomes much less noisy and our peaks are more resolved. We say we have better resolution. Okay, and now we can see, for example, here at about 95 ppm, that there's actually a signal here, all right, or maybe here. It's hard to tell. I can't even tell here. But with more scans, I can clearly see that we have a signal here at about 94 ppm. Oh, here we go. Peak labels are up here, 94.1 ppm. All right. Now with 65 scans, these 3 peaks here, which are kind of tall, they showed up pretty quickly. And we still see them down here. There's 2 tall ones here. And the one here at 138 is likely this one here. So that and those 2 showed up pretty easily up here with only 65 scans. Okay? Now if you look at this molecule, you would expect 17 different signals in the carbon NMR because you have 17 unique carbons. All right? You do have symmetry here. You might use that as an example to make sure you can determine number of signals. Okay? Carbon NMR. Also, here's a solvent signal, DMSO-D6. Not carbon, not acetone, sulfur, sulfoxide. An example of symmetry, these two carbons are identical, one signal. By the way, the deuterium is really irrelevant here. The H's would not give a signal. We could use regular DMSO and there would be no signal. Only carbon signals are going to be here. We use DMSO because typically you make one tube and then you run the proton and the carbon. But the carbons of the solvent give a signal. And the signal is kind of tall because we don't replace the carbons of DMSO. And since there's a lot more solvent in this tube compared to the solute, the compound, you're going to get a pretty tall signal compared to your signals for your compound. That's okay. But one thing I want to note is if we expanded it, this signal is 7 lines. Okay? Why does this carbon give 7 lines? Well, it's because of the deuterium. Now, if it's split according to n+1, it would be 3 deuteriums. n+1 is 4 quartet. 4 lines, 7. No. We have to know that I equals 1 for deuterium, not 1/2. The n+1 rule is really the 2I n+1 rule. Now this is some sort of advanced information, but to explain why this is 7 lines. Now if I equals 1/2, well, 1/2 times 2 is 1, so you can just get rid of that, and if when I is 1/2, this equals just n+1. But when I is 1, when the net spin quantum number is 1, what does this equal? This equals 2n+1. Okay? When I equals 1, it's 2n+1. Now we have 3 deuteriums, so n is 3. 2 times 3 is 6, plus 1, 7. And that's why the signal for the carbon of your DMSO-D6 solvent is 7 lines. Now you can't really see the 7, but if you look at the peak pickings, it's 1, 2, 3, 4, 5, 6, 7. There. Pretty neat, huh? All the signals for your compound are singlets because we remove coupling to proton. But we do not remove coupling to deuterium. So that's why this carbon signal is split. By the way, DMSO, this carbon here, gives a signal at about 39.5 in the carbon NMR, okay? Just below 40. Now I tell you that type of information at the very back of the handout here. Information about common NMR solvents. DMSO. In the Proton NMR, it gives a peak at 2.49. And that peak is for the residual solvent, or the residual hydrogens. In the Carbon NMR, DMSO gives a peak at 39.5. All right. And here it is at about 39.5. A little bit off. Whoever set the baseline here didn't set it exactly correct. I also give you information of where a water signal comes. Okay? In addition to the compound in this tube, there's probably also traces of water. Now, of course, water has no carbon, so you're not going to see water in the Carbon NMR. Okay? But you will see a water signal in the Proton NMR. At least a real one. Here was a real one back over here. We'll go here. The first one, remember the D2O shake? Cut off up here. But here is your water signal. It's about 3.3 ppm. Okay. That's what I told you right there. Okay. Usually a little broad. And indeed it is a touch broad there. Not as sharp as, say, these two peaks. Okay. Let's also look at this. This shows a difference between a Carbon NMR in which we have coupling to protons, and then B down here is a proton decoupled Carbon NMR. Here's the structure. Importantly, we need to know how many signals we expect here, proton and carbon. But importantly, we have to understand that this has symmetry right through here. All right. Ultimately, the answer is sort of shown here. Number of signals, 1, 2, 3, 4, 5, 6. And that's the same as that, and all through here. That carbonyl carbon is the same as that. That's going to give one signal. Okay? That's one signal. That's one signal. Hopefully you get the idea here. 6 signals. Here they are. Carbonyl. Okay, here's your carbonyl signal. Remember, way downfield, pushing 200 ppm. This one's at actually about high 160s. It's a little bit more upfield, 180, 200 is more typical. This one's a little bit more upfield than typical. Aromatics. Let's see, 7 per proton, thus about 140 for carbon. You see? It's aromatic region. And then you have these 2 saturated carbons. They're going to be more upfield. Just like proton saturated CHs would be more upfield. This looks like 2 doublets. It is 2 doublets, but I circled. That's 1 doublet and that's 1 doublet. It's 2 doublets, but they're sort of overlapping. And so here's 1 doublet, and then here's the other doublet. Okay? But why are they doublets? Again, we have coupling here. First off, the carbonyl carbon, there's no H. So there will be no splitting even when splitting is possible. It's a singlet. Let's look at the aromatic carbons. There's 3 of them. 3. We should have 3 signals. This one has an H. This one has an H. That one does not. 2 standard peaks. We would expect this carbon to be a short peak. Okay? 2 carbons. This carbon should be a doublet. It has 1 H bonded to it. 1 plus 2 is doublet. That carbon should be a doublet. 1 H bonded to it. 1 plus 2 is 2, doublet. And those are your 2 doublets for those 2 carbons. Where is this carbon signal? Which, by the way, should be a singlet, because there's no H there. Nothing to split it. Where is it at? I don't see it. Let's look down here. This should be, there's 2 H's on that carbon, so it should be a triplet. There's 3 H's on this carbon, so it should be a quartet. Here's your triplet, here's your quartet. Okay? The triplet is more downfilled because it's closer to the oxygen, and the oxygen de-shields this area, or this carbon. That looks very odd to me, because usually a carbon NMR is proton decoupled. And it's going to look like the one shown below, where everything is singlets. Okay? It's a little less intense. That's probably because it just was reran. It's not a consequence of the lack of splitting. But here's your carbonyl, still there. These 2 doublets are now singlets, but look right here. We're now able to see the signal for this carbon here. Because up here, they actually showed it to you, it's actually underneath the doublet. And this is one reason we remove the coupling, because it gives you better resolution of individual signals when you make everything singlets. We're able to see that peak now. So now we have 3 aromatic signals. The triplet became a singlet, and the quartet became a singlet. Question: why is that carbon so small? Why is the signal so small, so short? Well, that's an easy answer, and we've already addressed that. This carbon has no H, so it's going to relax slower. Since it relaxes slower, we're only going to get a partial signal. Now, the fact that this is so small makes me believe that the relaxation must be super slow for some reason for that particular carbon. All right, if a carbon has an H bonded to it, it's going to relax much faster. All right, hopefully that makes sense. Again, proton or carbon NMR, just about any NMR, you can get a flat baseline, and with a flat baseline you can see impurities, because otherwise there should be no peak. There's no reason for that little peak to be here, so we say it must be some other molecule or some impurity mixed in with this compound. Okay. Proton decoupled, standard carbon NMR. By the way, before we move on, this carbon NMR was run using chloroform D. And this triplet right here is from the solvent. Why is it a triplet? It's because it has 1 D. And net spin for D is 1, so the N plus 1 rule really becomes 2N plus 1. And so N is 1, that's 2. 2 plus 1 is 3, triplet. Now what's kind of a little bit odd is why is the chloroform peak not showing up down here? A little bit odd. I'm not sure what's going on there with that. It makes me feel like this is computer generated, or maybe it's just lower intensity, but still I would expect to see that there, like we see it here a little bit. Okay, in any event, let's start doing some practice here. By looking at some carbon NMR for different compounds. Number of signals. All right. Number of signals expected for this molecule. All right. And then let's assign them as much as we can. Benzene ring. There's no symmetry in the ring. All 6 carbons are different. We should thus have 6 different signals. We can actually number them. Carbon 1, 2, 3, 4, 5, 6. The carbonyl carbon would be 7. All right. And the methyl carbon would be 8. 8 different carbons, 8 signals. Here's this carbon NMR spectrum. We have 1, 2, 3, 4, 5, 6, 7, 8 signals. All singlets. Proton decoupled spectrum. Let's assign them. What is this here? It's your carbonyl carbon. Number 7. Aromatics. Remember, 7 to 8 for proton. 20 times would be 140, 160 for carbon. That's a little high. Okay, here's 140, 160. It's typically, aromatic is like 120, 160 for carbon. 6. Before we talk about that further, look down here. What is this here? That would be carbon number 8. It's your saturated carbon. And then we have 6 aromatic carbons. Okay, think about aromatic carbons. We're not going to be able to assign every single one. That's too difficult. We'd have to go to some tables. We may do that in a future lab. But one thing I want to point out here is that these 4 here are taller, and we have 2 short peaks here and here. We can assign those, not individually, but which 2 would be short? Well, it's the carbons with no H, and that would be carbon 4. There's no H there because we have a substituent. And carbon 6, there's no H here because we have the carbonyl substituent. And that's as much as we're going to be able to assign for the aromatic carbons until we have take a closer look at some tables, and we actually can do some calculations to assign these. But for what we're doing here, this is the most we can do. All right. That is indeed probably a computer-generated spectrum. There's no solvent peak. Okay. Now it also says indicate multiplicity of spectrum was coupled. For example, This signal would be a quartet if H coupled. And this signal would still be a singlet if H coupled. Because carbon 7 has no H. So even if you allowed for coupling, you would not see any coupling for carbon 7. Do the same for those. Also assign peaks for the next 3 spectra. You can also take a look at this actual carbon NMR. Okay. How many signals do we expect? Assign as many as you can. All right, see what other type of questions come up. I'm about out of time here. We will be working with carbon NMR. Also in this packet is a FNMR, Fluorine Nmr. You can do NMR on fluorine, it's less common. Basically, this is just a little kind of extra information, free information for you. I hope it may be of interest to you. If you're doing fluorine NMR, this compound's only going to give one signal. In this molecule, the fluorines are identical. All right, they're equivalent. One signal. Here it is. For standard, we can't use TMS because TMS does not contain fluorine. A common standard for fluorine NMR is hexafluorobenzene. And we set that at 0. And we say that this signal is downfield compared to our standard being at 0. Okay? But then you can take a look at this fluorine NMR. Here the fluorines are not equivalent. Okay, consequence of that, we do have splitting. Over here the fluorines split each other. That was that reference page. And then on the very back were answers to the warm-up page, which is on the front. Okay, guys. Please be doing some work with carbon NMR and be ready to ask questions and have discussion as needed on that. But ultimately, we need to move to start working comprehensive spec problems, such as were in the pre-course worksheet and in your workbook. Okay, guys. See you soon.